Right now, somewhere within a few hundred kilometers of you, there is a light switch. You flip it without thinking. The light comes on without a flicker, without a delay, without you ever wondering whether the power would actually be there. That confidence is one of the most expensive illusions in modern life. Behind every steady light switch on Earth sits an invisible balancing act, one that has to happen every single second, all day, every day, forever. Electricity is almost never stored the moment it's made. It's generated and it's used in practically the same instant. If you've ever wondered why blackouts happen, this is usually why. The balance broke, even for a second. Now scale that problem up. Imagine trying to keep an entire country's lights on, using power sources that don't even show up on a schedule. Solar panels that go quiet the moment a cloud passes over. Wind turbines that stop turning on a still afternoon. That is the exact problem engineers in China set out to solve, and what they built to solve it is so large, it's been carved directly into a mountain, using nothing more exotic than water, gravity, and roughly a decade of tunneling through solid rock. But here's the part most people never hear about. Every country racing toward wind and solar power runs into the same wall. The sun doesn't care when you need electricity, and neither does the wind. When renewable output outpaces demand, that energy has nowhere to go, and it simply gets wasted, switched off at the source. Grid operators call this curtailment, and in some Chinese provinces, it has meant losing more clean electricity in a single year than several countries generate combined. Build a grid on solar and wind without a way to store the surplus, and you haven't solved the fossil fuel problem, you've just built a less reliable version of it. That is the gap the Fengning pumped storage power station was built to close. Completed by the State Grid Corporation of China in Hebei province and brought to full operation at the end of 2024, it is now recognized as the largest pumped storage power station on Earth by installed capacity, a title it earned after more than a decade of construction. If you're into engineering stories about problems nobody else was willing to tackle at this scale, hit like and subscribe so you don't miss the next one. Why did the world wait this long to build something like this? The honest answer is that pumped storage isn't new technology. The concept dates back more than a century, and countries like Switzerland and the United States have used mountain reservoirs to store energy for decades. The idea is almost embarrassingly simple. Pump water uphill when you have extra electricity. Let it flow back down through turbines when you need that electricity again. Gravity does the storing. Turbines do the releasing. No lithium, no chemistry, no degradation curve counting down to zero. So why isn't the entire planet covered in these plants already? Because building one is brutal. You need a mountain with the right elevation drop, geology stable enough to tunnel through, 2 reservoirs worth of water rights, and years of excavation through solid rock, often half a kilometer or more underground. It is capital intensive, slow, and site specific in a way solar farms and wind turbines simply are not. You can bolt solar panels onto a rooftop in a weekend. You cannot bolt a mountain onto a power grid. For most of the last 50 years, that trade-off kept pumped storage as a niche solution, useful, but never built at a scale large enough to matter for an entire national grid. China's answer to that trade-off wasn't a new principle. It was industrial will, applied at a size nobody else had attempted. The site chosen for Fengning wasn't an accident either. Engineers picked a location roughly 180 kilometers from Beijing, close enough to feed directly into the Beijing-Tianjin North Hebei power grid, but remote enough to sit inside terrain with the right elevation drop between 2 reservoirs. Feasibility studies for the site began back in 2009, years before a single tunnel was bored, because in this industry, you don't get to guess wrong about the mountain you're building inside of. Here's the mechanism that changed everything. Fengning sits in the mountains of Chengde City in Hebei province, built around the Luanhe River. The plant works with 2 reservoirs, one high, one low, connected by tunnels bored through the mountain itself. When the grid has more electricity than it needs, usually overnight or during high wind and solar output, giant pumps push water from the lower reservoir up to the higher one. That water sits there, essentially as stored potential energy, for as long as the grid needs it to. When demand spikes, the water is released and gravity does the rest, rushing back downhill through 12 massive reversible turbine units, each rated at 300 megawatts, adding up to 3.6 gigawatts of total capacity. To put that in perspective, that is enough capacity to power millions of homes at peak demand, instantly, without waiting for a power plant to spin up. 10 of those 12 units are fixed speed. 2 are variable speed, the first of their kind deployed in China at this scale, meaning they can adjust water flow dynamically rather than running at one fixed rate. That flexibility matters more than it sounds like it should. A fixed speed pump is either on or off. A variable speed pump can fine-tune exactly how much power it's absorbing or releasing at any given moment, which lets Fengning respond to sudden swings in solar and wind output, almost like a shock absorber for the entire regional grid. According to figures cited by Chinese state energy media, the plant is projected to avoid the burning of roughly 480,000 tons of standard coal annually, while cutting close to 1.2 million tons of carbon dioxide emissions every year. None of this happens inside a small building. The underground powerhouse alone stretches 414 meters in length, stands 54.5 meters high, and is supported by a surrounding network of 190 tunnels totaling more than 50 kilometers. 50 kilometers of tunnel bored through solid rock, just to move water and house machinery. To manage that kind of excavation, without destabilizing the mountain above it, engineers used tunnel boring machines on key shafts, alongside systematic probe drilling and cement grouting to reinforce rock stability and keep the tunnels watertight. The construction itself began in June 2013, with the main civil works contract awarded to China Gazuba Group in April 2014, and the project was developed and is now operated by State Grid Xinyuan, a subsidiary of the State Grid Corporation of China, at a total investment of roughly 19.24 billion yuan, close to 2.6 billion US dollars. It took more than 11 years, start to finish, before the plant reached full commercial operation at the end of 2024, more than a decade underground, cutting through rock, to build what is essentially a battery with no chemicals in it at all. The steel and salt challenger nobody saw coming. Pumped storage isn't the only mountain-scale trick China has been building. While Fengning was proving that water and gravity could store power at gigawatt scale, a completely different approach was taking shape underground in Jiangsu province, this time using compressed air instead of water. The Guoxin Suyan Huayan Salt Cavern Compressed Air Energy Storage Project uses two enormous underground salt caverns, sitting between roughly 150 and 1,500 meters below the surface, as a place to store compressed air instead of pumped water. When there's surplus electricity, compressors force air down into the caverns under enormous pressure. When the grid needs power back, that compressed air is released to drive turbine generators, similar in principle to pumped hydro, but using pressure instead of elevation. With two 300 megawatt units and 2.4 gigawatt hours of storage capacity, equipment supplied by Harbin Electric Group, the Huayan facility became, on its commissioning in early 2026, the largest compressed air energy storage plant operating anywhere in the world, surpassing an earlier 300 megawatt compressed air plant in Yingcheng, Hebei province, that had briefly held the same title just a year before. It uses what engineers call adiabatic compression, meaning the heat generated during compression is captured and stored rather than wasted, reportedly pushing round-trip efficiency to around 71%, notably high for this kind of long-duration storage technology. The underlying idea traces back to research from the Institute of Engineering Thermophysics at the Chinese Academy of Sciences, whose compressed air storage work has since been commercialized across multiple large-scale demonstration projects. It's a different mountain trick, but the same underlying philosophy. Instead of relying on chemical batteries that degrade over a few thousand charge cycles, use the physical world itself, rock, salt, water, gravity, pressure, as the storage medium. Batteries wear out, mountains don't. And the pace of deployment tells its own story. China's cumulative energy storage capacity outside of pumped hydro reached over 144 gigawatts by the end of 2025, according to the China Energy Storage Alliance, with tens of gigawatts added in that year alone, spanning lithium batteries, sodium-ion systems, and these newer compressed air and gravity-based technologies working in parallel rather than competing for the same grid. The world starts copying this approach. This isn't a strategy unique to China anymore. It's becoming the direction the entire planet's grid operators are being pulled toward. According to the International Hydropower Association's 2026 World Hydropower Outlook, global pumped storage capacity surpassed 200 gigawatts for the first time in 2025, with a record amount of new capacity added in a single year. China remains the dominant force behind that growth, but it is far from alone. Japan and the United States rank second and third globally for existing pumped storage capacity, and both countries are actively expanding their own projects to support growing renewable generation. Switzerland's Nantes de Drance plant, completed in the Alps, uses the same core principle, an upper and lower reservoir separated by hundreds of meters of elevation, to store and release power on demand. India's pumped storage development pipeline has grown so quickly that the South and Central Asia region alone now has a project pipeline exceeding 300 gigawatts. Globally, the total hydropower development pipeline, including pumped storage projects at every stage from planning to construction, now stands above 100 gigawatts, according to the same IHA report, with more than 240 gigawatts of pumped storage already under construction worldwide. That is not a niche technology anymore. That is one of the largest coordinated infrastructure build-outs happening on the planet right now, and most people watching this have never heard of it. One research and development executive in the sector summarized the shift simply: as more of the grid depends on wind and solar, long-duration storage stops being optional infrastructure and starts being the thing that determines whether the rest of the grid actually works. That's not a China story anymore. That's every country that has bet its future on renewable power, all reaching the same conclusion at roughly the same time. The real-world proof point is already running. Fengning isn't a prototype or a pilot. It has been fully operational since its 12th and final turbine came online in 2024, meaning it has now had real years of continuous grid duty behind it. The plant sits directly in a region that services the Beijing area, and it was specifically positioned to help balance the grid, supporting the Beijing Winter Olympics push for a cleaner regional energy mix. It also sits next to a nearby wind and solar base in Zhangjiakou, with roughly 10 gigawatts of renewable generation capacity, which is precisely the kind of intermittent, weather-dependent power source that a plant like Fengning exists to smooth out. Every day since full commissioning, its operators have been running the same repeated cycle. Pump water up during low demand, release it during high demand, thousands of cycles by now, with no battery degradation curve to worry about because there's no battery chemistry involved at all. On the compressed air side, the smaller but newer Huayan facility is expected to generate close to 792 million kilowatt hours of electricity annually once similar projects reach full annual output, enough to power hundreds of thousands of households, while avoiding hundreds of thousands of tons of coal use each year. These aren't projected numbers on a slide deck somewhere. These are turbines spinning, water moving, air compressing, right now, today, as you're watching this. So how big could this actually get? China currently has more than 300 gigawatts of hydropower under construction, and roughly 218 gigawatts of that is pumped storage alone, according to the International Hydropower Association. That is a scale of construction almost impossible to compare to anything else happening in global energy right now. If even a fraction of that pipeline reaches full operation over the next decade, it would represent a jump in long-duration storage capacity larger than the entire current pumped storage fleet of most industrialized nations combined. China has also separately announced an action plan targeting more than 180 gigawatts of non-hydro energy storage capacity by 2027, backed by an estimated $35 billion in investment, covering everything from batteries to compressed air to next-generation long-duration systems. Layer compressed air, sodium ion, and other long-duration technologies on top of that pumped storage build-out, and you start to see the outline of a grid that can absorb wildly unpredictable solar and wind output without wasting it, and without leaning on fossil fuel plants as the backup plan. That's the real prize here. Not a single mountain battery, but a template other countries can build on top of their own mountains, their own salt deposits, their own geology. Now, the honest limitations, because the story isn't as simple as it sounds in a headline. Pumped storage only works where the geology cooperates. You need the right elevation drop, stable rock, and access to enough water, conditions that simply don't exist everywhere. Flat countries, water-scarce regions, and areas without suitable mountains are largely locked out of this specific solution, no matter how much capital they have. The construction timelines are also brutal by energy industry standards. Fengning took roughly a decade from the start of construction to full commercial operation, which is an eternity compared to how quickly a solar farm or battery storage container can be deployed. That means pumped storage is a long-term bet, not a quick fix for a grid that needs flexibility this year. Engineers on comparable Chinese pumped storage projects have also had to contend with high in-situ rock stress, fractured surrounding rock, and in some cases, high altitude, low oxygen working conditions, all of which slow construction and add cost regardless of how much capital is available. There's also a real cost and access gap. Wealthier nations with strong state backing, like China, can fund decade-long underground megaprojects at a scale that most developing economies simply cannot finance on their own. And even compressed air storage, while faster to build in some cases, still depends on finding the right underground salt formations, which aren't evenly distributed around the globe either. None of this undercuts what's already been proven to work. It just means the gap between what's technically possible and what will actually get built everywhere on Earth is still wide. And closing that gap will take decades, not years. Which brings it back to that light switch. The one you flipped without thinking, the one that worked instantly, the one you never had to question. Underneath that small, unremarkable moment sits an entire hidden industry racing to keep it boring, keep it reliable, keep it invisible. Fengning proves that some of the biggest problems in modern engineering don't need a radical new invention to solve them. The physics behind it was understood over 100 years ago. What changed wasn't the science. It was someone finally deciding to build it at a scale large enough to matter for an entire national grid. Sometimes the biggest breakthroughs aren't new ideas at all. Sometimes they just need someone willing to dig a hole half a kilometer into a mountain and commit to gravity doing the rest. If stories like this, engineering solutions hiding in plain sight for decades before someone finally builds them at scale, are the kind of thing you want more of, hit like, subscribe, and turn on notifications so you don't miss the next one. Before you go, here's a question worth sitting with. If a solution this old, this simple, and this proven was sitting unused at this scale for over a century, what other boring century-old ideas do you think are still waiting for someone to finally build them big enough to matter?